you hear?
Okay. Yes, now I hear. Let's see. I think we can wait for a few minutes.
Can you see the slides?
Yes, I do. I think. You're in Paris now?
Yes.
Okay.
I mean, a bit outside, it's in the suburb, 20 kilometers away.
Right.
I'm at home because at the institute we don't have good place
Sure.
for not disturbing other people when making a talk.
Mm-hmm. So what is your status right now? You're in Saclay, France? Or? Okay.
Yeah, so I had this Marie Curie fellowship. I don't know if you know them. So I had one which where the deal is to go 2 years outside Europe and 1 year inside. So I went to MIT and IAIFI during the first 2 years, and now I'm at Saclay.
I see.
But in fact, it's a mixed position between the different places.
So the fellowship is for the string theory or for the machine learning? Or?
It's so the fellowship itself, it's every field. Mine, I did it on machine learning for string theory. But you can write projects for
Sure. But no, yours. I mean,
okay.
Right.
Sorry. Okay. Yeah. Mine was machine learning for string theory. And there is also a second part which was trying to get cubic action for string field theory.
Right.
So I was mostly working on these two aspects.
Mm-hmm. So let me see. Mm-hmm. No, I have admitted any request almost any. So there is no request that I have not accepted. So, okay. I see. Sure. Okay. Shall we start? Okay, it's a pleasure to have our string theory group meeting today online with Harold Erbin. Harold Erbin obtained his PhD in theoretical physics from Sorbonne University in 2015 and achieved his habilitation.
شما صدا ندارم.
Can you hear me now? Everyone can hear me?
Yes.
Yes.
So can you hear me now, Dr. Garsi? Mohammad Reza. Okay. He achieved his habilitation at Paris Cité University in 2021. He is currently a Marie Curie Fellow at MIT and IAIFI Boston and CEA List Paris. Besides working at the intersection of machine learning, physics, and mathematics, his interests include string field theory, two-dimensional gravity, black holes, supergravity, and tensor models. I should also add that he is the author of quite a recent book on string theory that you can Google with his name. Harold, over to you. Just one thing: if there was a interruption in the meeting or whatever happened, please use the same link to rejoin the meeting. Please go ahead.
Sure. Yeah. Thanks. Thanks a lot for the nice introduction and for the invitation to speak. So I will present this work on building string field theory using machine learning. And I will start with an introduction on string field theory and machine learning. So so the hope is to be very pedagogical. But in case you have any question, please interrupt anytime. I mean, we can keep this simple and with a lot of discussions. So first, I would like also to thank my collaborator at ACAN, with a PhD student of Barton Sribar at MIT and IAIFI, with whom this paper was made. And okay, so let me start. Okay, so I will start with a general introduction just to explain where I want to go and what are the main keywords of the talk. Then I will continue with a general introduction to string field theory. So trying to explain the general concept and focusing in particular on the mathematical structure we will need to explain how we build the action and why we need machine learning. After that, I will introduce some general ideas in machine learning. And then I will really enter in the core of the paper, which explains the idea of minimal area string vertices and how we use machine learning for string field theory. Yeah, and then I will conclude with some perspective. So the idea would be to go to make the first two introductions, and then maybe make a break, and then we continue. So depending on how time goes. So first, I will start with some highlights of the talk to give the keywords which are important and explain so in which direction we are going. So first, what is string theory? So it's a second quantized formulation of string theory. So it means that we try to make it close to usual QFT for point particles. And the second important concept is that amplitudes correspond to the 2D CFT correction function integrated over moduli space of Riemann surface. So this mathematical structure here of Riemann surface will appear everywhere in string field theory. So it's very important. So we spend some time explaining it. Now the idea is that in string field theory, the interactions are called vertices, and they are characterized by some geometrical properties, which offer some local coordinate page on the Riemann surface, and second by some subspace of the moduli space. Now the idea is that you have a set of interaction in your action. You can write Feynman rules, and at any given order in the H bar and in the number of external states, the sum of Feynman diagrams must provide the cover of the moduli space. So in string theory, you have this nice duality between what you do in general QFT, so Feynman diagram and so on, and covering of moduli space. So you can, in many cases, just translate your question to geometrical questions. And so at the classic, how you get the string vertices? So you have many possible choices. And arguably, one of the simpler choices is the so-called minimal area vertices. Because you can show that they satisfy some nice property, and there is some general theorem about how they can be built and so on. And in particular, at the classical level, they are made from Strebel quadratic differential, which I will introduce in detail later. And the point is that if you can compute this differential, then you can compute everything you need in string field theory. And this differential is very simple because it just depends on the so-called accessory parameters, which are related to the uniformization of Riemann surface, which are just complex parameters, and you have as many as you have of moduli. And so the idea is that it's much simpler than just finding local coordinate patch or moduli space, because it's just a finite set of complex parameters. So when you have these accessory parameters, you can extract all the data you need, so local coordinates and vertex regions. Now the point is that this is still a very hard mathematical problem. And so what we did in our paper is to use neural networks to parameterize the accessory parameters and the vertex region. So which really simplified the computation. Okay, so here was the general highlights. So now let me introduce in a bit more details string field theory and what we do. So the usual formulation of string theory is a worldsheet formalism. So which is really like the word line you have for point particle. And it's a first quantized formalism. So it means that you can describe the dynamics of a few strings naturally. And it's a bit cumbersome because you have various problems. So in particular, it's on shell, you have some divergences, and it's intrinsically perturbative. So it's not a nice formalism. So in particular, if you look in QFT, we almost never use the word line except in few particular problems where it can be quite powerful. But in general, we just want to use second quantized field theory and just work with that. So now string field theory is exactly that, so a second quantization of string theory. And the advantage that you can use the modern language and tools of field theory, so like renormalization, you can go off shell, and so on. Another advantage that it's a constructive framework and the symmetries are manifest. So it's also a bit nicer to kind of understand the deep structure of string theory. You can use it to prove consistency of the theory, so in particular unitarity, analyticity, or finiteness. You can study background. So the most important is the background independence, because as you know, one of the main criticism of string theory is that it's not manifestly background independent. But at least with string theory, you can show that it doesn't depend on the background. So it's really a nice and important result you can get with string theory. You can also study background with flux, which you cannot do easily with standard formalisms. In particular, you can study perturbation of, for example, a Minkowski background with Raman flux. You can also study background with the instantons. And finally, it also gives you tools to compute amplitude and effective actions more efficiently. So what are the problems now with string field theory? Because if it was if it were very simple, we just all use it. So first, that the action is non-local, non-polynomial, and has an infinite number of fields. So it's quite hard to deal with. So basically, we have the choice between dealing with some general state in a very big Hilbert space, or with an infinite number of fields with S properties. So it's a bit hard to deal with. And interestingly, it's because the string fields is a functional and not a function like fields of point particle. And the second problem is that the general properties are known, but not the explicit form. So it's quite hard to do computation and extract number from string field theory. So it's why it's very important to develop new tools to really be able to make computation and get new results you cannot get with a worksheet. So how do you get string field theory? So first, as I was mentioning in the highlights, you can see on-share amplitudes as taking Riemann surface moduli space and integrating a correction function of a 2D CFT over this space. So, so you can see the 2D CFT as giving you a map between moduli space to string amplitudes. So now, if given this map, how do you get off-shell string amplitude? So the idea that you will again start with the moduli space and you will decorate the surface with local coordinates. So when you take these two geometrical data, now you can use the 2D CFT to map to off-shell string amplitudes. Now you can try to add even more data. So you take this moduli space and the local coordinates, and you introduce a decomposition of the moduli space by sewing or gluing of Riemann surface. So the idea is that you can see, instead of seeing each surface as being independent in this moduli space, you can take two surfaces and say, okay, what happened when I glue them in some way? And so you can look at all the possible way of gluing, and it will give you some subspace. And you will get also some surface you cannot obtain in this way, you will get another subspace. And the idea is that decomposing the moduli space in this way gives you what is called the geometric BV algebra. So BV is for Bataille-Vilkovitsky. So it's a geometric version of the BV algebra we find in BV quantization of QFT. And so now when you use the 2D CFT to map this structure, you get a string field theory, which also is a satisfies quantum BV master action. So which implies that the theory is consistent at the quantum level. And now you can also see the 2D CFT as providing a BV morphism between different BV algebra. And if you want to understand on the QFT side, so in fact, the string field theory, you can see it as a decomposition of off-shell amplitude in terms of Feynman diagrams. So as you see all the story you have in normal QFT, you also have it in the geometrical side. And the important point here is that, as I will explain in more details later, so you can see the 2D CFT as the background of your string theory. So all the information which is on the left of the arrow is background independent. So anything on Riemann surface moduli space, BV algebra, local coordinate, and so on, once you have built them, you can use it for any background. You don't need to know more. And in this way, you also have a decoupling between what you need to do. So you need to understand this geometry, and then you need to know your CFT. And if you know the two, then you can compute pretty much what you want. And so in that sense, it's very important to be able to understand better the geometrical data because like you can just reuse it every time. Okay, so now some pictures to give a better idea of what's happening here. So first, let's look at the picture in the left top corner. So this one here. So here it's a general Riemann surface with two punctures and two holes. And so what we do when we want to move from on-shell to off-shell amplitudes, we take this Riemann surface and we add local coordinate patch on each puncture. So here on these punctures, I have one patch, which I'm describing as a function mapping to the unit disk. Here I have another patch with another transition function to the unit disk. So you do this for each surface in your moduli space, and then you can show that this is sufficient to describe off-shell amplitudes. Okay, now let's move to the decomposition of the moduli space. So so here I'm just having a pictorial representation of a moduli space. So each point in that space is a different Riemann surface. And now you introduce this decomposition by grading. So what do I mean by that? So now you have two types of surface, which you can also see as Feynman diagrams made of cubes. So for example, here in the bottom right corner, you have a 4-point interaction between strings. And here you see that you can interpret this as two strings interacting, creating a new string which propagates. And these strings again split into other strings. So in terms of Riemann surface, you can see this surface as one surface made of two pieces connected by a long tube. So the two surfaces you get will be like we come from other moduli space, so you can just take them, glue, and you get new surface. And a second type of surface, or for example like this, so where you have four strings which interact in a quite localized way. So here in this process, you have no way of saying that there is a long tube or some intermediate string. So here the difference between the two diagrams is like in QFT of 5 cube plus 5 4 theory. When you have such theory, you can either have two particles which interact, propagate, and decay, or you can just have four particles interacting in the same place, and the kinematic is different. And the point that you have exactly the same kind of ideas in terms of Riemann surface. So at the end, you will get your moduli space will split in this way. So you have different parts with propagator graphs and one part for the vertex region. Okay, so now, so what are the objectives? So from the point of view of physics, so the idea is to use machine learning to extract numbers from string field theory and in particular understand better the clustering vacuum. And from a math point of view, what we want to do is to construct function on moduli space of Riemann surface and subspace of this moduli space using machine learning. And so I will explain later in the talk why we need machine learning to solve this problem. Okay, just is everything clear for this introduction? Or should I expand on some points? Okay, so if everything is clear, let me move to the application we have in mind. So as you may know, there is a very big question mark about the status of the closed-string tachyon vacuum. So for the open string, in bosonic strings, you have tachyons in the spectrum. And it's very well understood in the open strings, which just means that so the space filling the branes is unstable because it doesn't carry any charge, so it can just decay. So the presence of the tachyon, it describes the instability of this brane. And when you go to the tachyon vacuum, it just means you have no branes and you have no open string excitation because there is no branes to which they can attach. So this is well understood. Now the closed string also has a tachyon, and it's not clear what its status. So some people have argued in different sense. So if you have a minimum, if you can write its potential and you have a minimum, it just says that we need to roll there and we need to understand the physics on that minimum. So what does it mean in terms of space-time and so on? Some people think that you don't have minimum or just at the infinity, which means that closed bosonic strings would be sick and ill-defined. But in practice, no one knows. So there were some preliminary studies, but there was not the tools to readdress this. So how you do it in principle? So you perform a very truncation of the string field. So it means you just keep the string states up to some mass, because higher and higher the mass, the less they will contribute to the potential of the tachyon. Then you compute the potential up to some order in the string coupling, including all the states you have kept. Then you integrate out all the field except the tachyon and the dilaton. And you compute the vacuum and you do an extrapolation in level and order. And in this way, you can try to get an idea of where is your vacuum moving. So here is the form of the tachyon potential if you just truncate all the field except the tachyon. So you get something of this form. And so using our method with machine learning, we found that the quartic term is around 72.32. Knowing that previous results are at 72.39, So it shows that our method gives consistent results. Also knowing that we didn't try to fine tune the numerical precision because we just wanted to illustrate that it works. And as I said, once you have this geometrical data, you can just apply it to any background. So for example, you can consider twisted tachyons or something like this. So what we will hope to do here with this new tools is to develop ways to compute effective potentials and later effective action of co-string field theory at any order. I mean, at some large order from which you can really make prediction about problems like the co-string tachyon vacuum, which you cannot do using standard worksheet techniques. Okay, so is there any question for the introduction? Okay, so if not, I will move to an introduction on string field theory. So first, what is a string background? So a string background is made of two parts. So the first is a 2D CFT. So the 2D CFT is really what defines your spacetime. And it's made of three pieces. So the first is a conformal invariant nonlinear sigma model with the non-compact scalar fields, x mu. And this nonlinear sigma model will describe a spacetime with some metric g mu nu and d non-compact dimension. Then you have some generic internal matter CFT with some central charge C int. So here you can use this to describe some compactification or even some non-geometrical like degrees of freedom. So for example, if you take d, you can take 26 minus d dimensional torus, and you will be there. So here it's everything which has not any non-compact eigenvalues like the spacetime momentum. And then you have a BC CFT of anti-commuting ghost with central charge minus 26, which come from worksheet reparametrization. So here it's what characterizes your CFT. Then you also need to specify the string coupling as part of your background. Okay, so now what you can show using string field theory is that if you move, you change your CFT or you change the string coupling, you can just interpret this as expanding the string field on some classical solutions, plus making a field redefinition. So it's really just the same theory, but written in different variables. One way of thinking about this formulation is like if you take general relativity, where you expand the metric in some background metric with h mu nu, it's exactly what you would get here. So first, okay, so total central charge should be 0. So basically, it tells you that the internal central charge should be 26 minus d. And if you take free scalar fields, you just get a flat spacetime, which can be Minkowski or the flat Euclidean plane, depending on the signature you choose. Okay, now let's move to the string field action. So what is a string field? So a string field, it's a general state in the first quantized CFT Hilbert space. So you have your 2D CFT, and in general, you have some Hilbert space associated to it. So for example, in the simplest case where you just have ghost and scalar field, you can read it as a Fock space. And you have many states, and now the string field is just a general linear combination of all the possible states. So it will include the tachyons, the gravitons, and so on, with all the fields. So now in co-string field theory, we have the so-called level matching constraints, which tells you that the string field, and in fact any state in H, should be killed by B0 minus and H0 minus. So this constraint comes from when you parameterize the worksheets. So on the co-strings, you have the sigma coordinates, which describes the spatial direction on the co-strings. But because the co-string is is a closed line, you don't have any natural origin, so you have kind of some gauge symmetry, and you need to fix some origin. And the idea is that H0 minus is so it's symmetry generators of this symmetry. So when you fix an origin, you need also to remove this generator of the spectrum. And the B0 minus is a ghost, Faddeev of ghost associated to this symmetry, so you need to also remove it. Okay, and so here, so I assume that most people should know the worksheet, so string theory. So there is 0 plus minus, B0 and C0 are just combination of the modes. Okay, I forgot to put plus minus in here and here. Okay. So now what is a quantum BV action? So you can write it in this way. So first you have a kinetic term, so quadratic in psi, where QB is the first quantized BRST operator. So it's also the BRST operator you can use to determine the so the physical state in the standard worksheet formulation. And then you have an infinite number of interactions for also all G, where G is the genus of the Riemann surface. And as you see, it's also the group counting parameter. So at G equals 0, you have the classical interaction. And then for G greater than 0, you have terms which you can interpret as counter terms. And the nice point of string theory is that all these terms are by definition finite. So you have some renormalization from all the G different than 0 terms, but all these counter terms are finite. You can really compute everything from first principle. Okay, so now in terms of the structure, so here in the kinetic term, we define this the inner product by the BPZ product together with the C0 minus insertion. So why this 0 minus insertion? It's because so we have the Gauss number anomaly in string theory, which tells you that the Gauss number of any term should be 6. So I didn't write it, but psi has Gauss number 2, QB has Gauss number 1. So here you have Gauss number 5, which means you need one additional C ghost. And here we get C0 minus because C0 minus is a conjugate variable of B0 minus. So if you have this insertion, you make sure that this constraint is valid for the state interaction. Okay, and then now, so you have a fixed psi, which is a general state in the Hilbert space. So it means you cannot just multiply it like you do in standard QFT, where you have some fields. Here you have some structure, so you need to give some ways of combining the structure of different fields together and getting a C number. In standard QFT, it's like when you have a gauge field, you need to explain how you contract the different mu spacetime indices. And because you have a spacetime dependence, you need also to integrate over T to get a C number. So here the goal of this VGN is just some generic function which take n states and gives you some number. So the difficult part of string theory is really being able to characterize this VGN here. Okay, so now the notation might look a bit unfamiliar because you can say, okay, what is here this inner product and this QB and like of this function and so on. So just to give an idea of why we use these notations and what they will mean, consider a 5-4 scalar field. So here we have the Klein-Gordon kinetic term, and then we have the standard 5-4 written in momentum space. So we can rewrite this action in a much more compact form in this way. So here we have some inner product, phi, a kinetic operator k, and here we have a quartic function b4. So what does it mean? So first, here we have phi, which is a ket field. So to write this ket field, we want to introduce a first quantized moment, so a basis of first quantized momentum states. So imagine if you do, so if you look at the word gun, you have one particle. You can quantize it using the Schrödinger equation, and you look at the eigenvalues, and the eigenvalues will be just plane waves. So this ones here are the plane wave. And now you can write a general state by taking a linear superposition of plane wave with some arbitrary function phi of k. So now in the first quantized theory, you also get a natural inner product between plane waves, which just tells you that it gives you a delta product k plus k prime. So you can interpret it as momentum conservation between plane waves. So the kinetic operator k is just a Grant-Gordon operator. So you have p squared plus m squared, where p squared is an operator. So when it acts on k, the eigenvalue is k squared. So you recover this. Now you see in the first term, okay, plug two fields phi with k and k prime. You act with k, you get these factors. Then the inner product gives you a delta function, so you recover indeed the first term. Now for the quartic vertex, you define it in this way. So the idea is that first you write the phi. I mean, you insert this expression for the ket phi. And by linearity of V4, you can just take this C number field outside this V4. And we define the V4 of K1 to K4 as the value of this function here when you apply it to state in the basis. And to recover the previous expression, we just have to say that when we evaluate this function with K1 to K4, which are momentum eigenstates, we get a delta function conserving momentum. So as you can see, we can just use the two notations. So it's our first quantized notation, or more like intrinsic field theory notation. The point is that for string field theory, we didn't manage yet to find a like proper QFT notation, so where we don't have to use the first quantized formation. And it's related to the fact that we need to specify the background to make any computation or definition. So you see here, here QB is background dependent. So even the linear superposition of state is background dependent. So as soon as we start to introduce this background, we are kind of stuck with all this thing of using get and this function. So one of the big goals of string field theory is how you can move from this notation, this notation here, to something more like this, where you don't need to remember what was your first quantized theory, because this has much more chance to be background independent. Okay, so now to get the Feynman rules, we need to first do gauge fixing. So the simplest choice you can do is the Siegel gauge, which read B0 plus on the string field is 0. So why this choice is very simple? It's because it's the one you naturally find in the worksheet formalism, for example, when you want to compute the BRST cohomology. And it's also the one you get when you do the old school covariant quantization. And it's the one you get also for the amplitude. So it's kind of the simple choice, but you could choose another one if you want. In that case, the kinetic term takes this very simple form. So where the QB is replaced by C0 plus H0 plus. So now you can write the propagator. So you just need to invert the kinetic term. So you get B0 plus, B0 minus, and H0 minus plus. You can also write the fundamental G loop endpoint vertex like this. So it's just given by the VGN, which you evaluate with the different external states you want to consider. So, okay, all this was again a bit abstract, but you can make it even more intuitive and closer to QFT by expanding the string field in Fourier modes. So when you expand phi, when you do it in QFT and you want to expand a field, you just find an integral over k, and that's all. So the reason is because your field is a point particle. So when you do the Fourier expansion, you expand the x, which describes its position in space-time, and it's related to the momentum, which is the center of momentum, the center of mass momentum. So you just have this. But now when you have the string fields, so you need to do a Fourier expansion for two things. So first, so the string is extended. So you have also a position which corresponds to the center of mass. So when you do the first Fourier expansion, we get a continuous variable k, which is the momentum for the center of mass. But now, because you have an extension, you also need to do a second Fourier transform on the line, which will give you a set of discrete modes. So because spacetime is not compact, so you get continuous momentum. The line is finite, so you get discrete modes. So it's why when you expand the string field over states, you will get two sum. You get a sum over some discrete indices, which can be Lorentz indices, some group representation, KK modes, and so on. And you get an integral over the continuous momentum. So now, given this expansion, you can write some 1PI actions. So here you have kinetic term with some kinetic operator KIB. And then you have a sum of interactions which go from n equals 0, so cosmological constant, to tadpole, mass renormalization term, and so on. So the idea here is that when you write this, is that in this Vn, you have really some all the quantum corrections already. So now in this momentum representation, the propagator is just the inverse of the kinetic term. And it will take this form, so you can work in the basis of states which are eigenstate of the momentum operator. So in that case, you will get something which is 1 over k squared plus m squared, which is just the standard propagator from Klein-Gordon. You will get a mixing matrix for states which have the same mass, and then you can also have a polynomial momentum like you get, for example, for the fermions or photons and so on. So the vertices will have this general form. So they are given by the integral over a finite set of complex variables t, which are the moduli of the Riemann surface you look. So they will be integrated just in the vertex region I was explaining before. And you will get an exponential term. And here's an exponential term, sorry. And some polynomial which will depend on the moduli parameter and momentum. So here it's interesting because here it's polynomial, so it doesn't have any poles. Here it's an exponential with a minus sign, and you can show that the kind of metric which appear here is positive definite. So it means that this vertex, you can prove that there is no poles. And because you have this exponential damping factor, it will converge if you integrate over any combination of k. So the only problem you can get is that when in Lorentzian signature, you get a plus sign for the energy. So you can get some divergence here. So I will explain later how you take care of this. The second point that you also have an exponential of minus c and the sum of the mass. So it means that the higher, so for very massive states, you get also some damping factors. So even when you consider after Feynman diagrams which have an infinite sum over infinite number of states, it will contribute less and less because of this exponential factor. So it's how string field theory makes explicitly finite any amplitude in string theory because it makes, we can see there's two factors. So now you can combine all this together to write a general truncated Green function. So you can show that the Green function will be the sum of a Feynman diagram of this form. So you have an interaction over moduli parameters in some region. And you know that this region will exclude any divergence from this expression. So like this integral over moduli will be finite. You have an integral over loop momentum. So the loop momentum will appear, first here. So in this P, which is a polynomial, so it's fine, no divergence. I'm sorry, it could diverge, but then you have this exponential factor, and you can show again that this GRS is positive definite. So in general, it will converge for spatial momentum, and it will diverge for Lorentzian energies. And you have the usual poles from the propagator. So as you can see, just like very standard QFT amplitudes, except for this exponential factor. So one way to get an intuition on string field theory and try to derive properties to say, you just forget about everything else, like all this Riemann surface and CFT and so on, I would just start with green function of this form and ask what can I derive something. And as I will explain later, with this you can really go quite far, so you can prove soft theorems, unitarity, and so on. So you can really do a lot just by knowing that amplitude should have this form. And the second point, that if you prove something for a theory of that form, you know that any other theory of quantum gravity which has the same Feynman diagrams will also have the same property. So you can really prove some general theorems in this way. So how do you define momentum integration? So the idea is that you cannot define directly your amplitude and green function in Lorentzian signatures because of this exponential divergence. You cannot do also like a standard weak rotation.
Can I ask,
yes.
so what is the imprint of the quantum gravity in this Feynman diagram?
Yes. So here the imprint will be hidden in the fact that somewhere here you will get propagators from gravitons and momentum here which come from gravity. In fact, you don't need gravity inside this. You can just consider some generic QFT without gravity. But in practice, for perturbative gravity, it just also fits that form.
Okay. So you this is a generic form for any gravity, I mean quantum gravity, let's say amplitude.
Yeah, so not any quantum gravity amplitude, for some class of amplitudes. So for example, like here the fact that you get this exponential factor is a bit specific to what you have in string theory and maybe also higher spin. So if you have a quantum gravity theory which perturbatively gives you something which is not of this form, then it will not fit. On the other hand, something you can do is to try to replace this exponential by some general function which satisfies these properties. In that case, it would also work, because you can show that really what matters is the behavior of these factors when the momentum go to infinity.
I see. Thanks.
So yeah, just to clarify, it's not any theory, but it's a large class of theories you can describe in this way. Okay. So now how you define the momentum integration. So okay, weak rotation, normally you cannot do it, because so in normal weak rotation you start with the Euclidean signature and then you just rotate the contour, but then you will get a problem when you want to integrate over the energy. So you need to do something else. So here there is a generalized weak rotation from Pius and Sen. And so the idea is to define the green function for Euclidean internal and external momenta. So you just take everything Euclidean, and you do an analytic continuation of the external energy and integration contour in a continuous fraction. But you always keep the poles on the same side of the contour, and you keep the ends of your contour at plus minus I infinity. So in pictures, it's here. So you start by defining your amplitude with some external states, and let's say your poles on in that place. The contour is on the imaginary axis, and now you start to continue your states from Euclidean energy to Lorentzian energy. And so what we know is that these poles will move to the real axis. And so what you do is that you always keep the contour so that, I mean, poles don't cross. So you get something like this because you want to keep the ends fixed there. And so this prescription gives you also the standard weak rotation when it's right defined, because what you can do is that you start. Sorry, the mouse work. So what you can do is that so you start your contour here at the bottom, then you go at the very end here, you run around the real axis, and you stay on each side of the poles, and you avoid your poles and so on, and then here you go back up. Now the segments you have here And here, from the argument of weak rotation, you can remove them if you don't have any poles. So this is real generalization, and it also work for more general case. And you can use this prescription to show various things. So, for example, you can show that your expression is analytic for the spatial momentum real and for the energy in the first quadrant. So where you must keep an imaginary part for the energy. And here, in fact, you can understand this imaginary part, which can be as small as you want, as a I epsilon prescription, which you have in any case when you do the standard weak rotation in normal QFT. So as your I epsilon helps to move the poles a bit away the axis. So to summarize, so what is string field theory? So you can see it here as a standard QFT with an infinite number of fields and Hawk speeds, infinite number of interaction, non-local interactions, and they reproduce watching amplitude when the latter are well defined. So already moving from like the general action, which is very complicated and Riemann surface and so on, to this perspective, can give a lot of intuition about like how it works, what you can expect, and so on. And then the second step is to remember that you can translate most of the language of QFT to some statement on Riemann surface. And this gives you also some intuition about the geometry. And I want to say two consequences of non-locality. So the first, that we cannot use position representation. And we also cannot use the assumption of local QFT like micro-causality and so on. So it means we need to prove, again, most of the consistency property. So in parallel, what can we prove? So as I mentioned, we could prove, I mean, when I say we, it's a community, not me. We can prove background independence. Using the generalized weak rotation, we can prove the Kutkowski rules and show that it implies unitarity. We can show that it also gives you a space-time I epsilon prescription, which is also equivalent to the moduli space I epsilon from Witten. You can prove primitive analyticity and crossing symmetry. You can also get soft theorems. And yeah, so like there's four things, as I mentioned, because it in general applies to quite general QFT, having the same form as string field theory. It's valid also outside string theory. Now, what kind of remains to understand better is the idea of locality, causality, and CPT. So CPT should be quite easy to prove, but it's still not really clear how you can define locality and causality. One reason is because like most formulation of both look too simple in the sense that it's very hard to find a counterexample, or they are formulated in a way where you cannot really compute. So overall, it's like it's not clear how you can define something which is non-trivial here and show that what you get for string field theory. The main point, which is still notable, is that crossing symmetry, or better, like primitive analyticity, in standard QFT, it's a consequence of locality. So in general, you use locality to prove primitive analyticity. Here, we managed to prove primitive analyticity directly from poles in Feynman diagrams. So it's kind of hinting that string field theory should not be too bad with respect to locality, but we need more work for this. And the nice other point of this generalized weak rotation is that you can also use it to prove the consistency of the time-like Dublik theory, because you have some iteration over momentum with similar properties. Okay, for the link. Okay, so now that I made the general introduction to string field theory, I will go in more details to like the structures of the amplitudes and of the string vertices and how we try to compute them. Before that, is there any question on the previous part? Okay, so no question. So let me describe off-shell trivial string amplitudes. So an endpoint string amplitude with external state AI has this form. So first you have an integration over the full moduli space M0M. So here 0 says that it's genus 0. So it's the spheres with n punctures, which we take to be at x1 to xn. So what we integrate is a cohesion function in a 2D CFT, which lives on this sphere with n punctures. So what is a moduli space and what does it mean to integrate here? So the moduli space is really all the spheres with n puncture which are inequivalent topologically. So you want to sum over all these different combinations. And this comes from the fact that when you do the worldsheet path integral, you want to integrate over the fields living on the worldsheet. So you have the worldsheet metric and you have the other fields of like the scalar fields. And when you want to integrate over the worldsheet metric, you can do a gauge fixing to remove the reparametrization. And what remains is what you cannot fix by reparametrization, so it's a topology. So this integration here is the remnant of this integration over the worldsheet metric, and you just get topological parameters. So now the point is that on the sphere, you can use the SL2C invariance to fix 3 points. So we fix the last 3 at 0, 1, infinity. So in practice, the integral is only over n-3 variables. And you can also show that the moduli space of the n-puncture sphere is just n-3 copies of the complex plane. Next, we have some ghost insertion here, which I don't want to describe. So they have 2 roles. So the first is to give a measure of integration over the moduli space. So you don't have a flat measure, but you have something more complicated. And the second is that they are needed for the BAS invariance. So like 1 and 2 are really related to each other. And then here you have your states AI0, so which are inserted in some local coordinate patch. So we have a picture after for better clarification. But for unchained amplitude, okay, it's saying that it will close. I will not finish my sentence and join back.
Yeah, please, if it ended, just use the same link to rejoin. Sorry, this is
no problem. See you soon. Now?
Yes, sorry for the interruption.
Yes.
Yeah.
Yes, sorry for the microphone. So yes, so I was describing this expression here and focusing on this last part here. So in normal worldsheet amplitude, you would just get the sum of the product of all the vertices, which you insert at different positions. For example, for the 4-point amplitude, so 3 states would be fixed at 0, 1, infinity, and the last one will be over Z4, and then you integrate Z4 over all the surface. Here you do something a bit different. So you do so instead of so insert the operator at 0 in the unit disk, and then you use this transition function to bring the operator in the unit disk back on the surface. So we have a slide later. So now like this transformation of weak conformal maps. So for example, if you look at AI, which is a primary state, so which is the case when it's on shell, so you can write it in this form. So you see that the conformal transformation of AI at 0 will be AI evaluated at the conformal map at 0. So now if you say that the conformal map at 0 is just the location of the puncture, you just get the standard on-shell result for that part. And here for on-shell, H is 0, so these factors disappear. So you see that it's really just a rewriting of on-shell amplitude, but in a bit more complicated way. And the idea is that now it generalizes also when A is off-shell. So let me, oops, sorry, make one. Yeah, so yeah, the mouse was not on the right screen. So I was saying that here you see that you get, so this factor disappears when H is 0 for an on-shell state, and this becomes the location of the puncture. So another way to display it more clearly, so here you see that you have a sphere with 4 punctures. You have a coordinate patch on each of the punctures. And now you will insert the state at the origin of the unit disk, so 1 for each state. And then you use as transition function F1 to bring the unit disk inside this patch. And why we need to do this for shell? It's because the SA2 invariance is broken when states are not on shell. And why it's broken? Because of the puncture. So the idea is that the punctures will give you some spike of curvature, which you don't see when you're on shell, but when you're off shell, it's really there. So what you want to do, you want to work on the unit disk where the metric is locally flat, so you can just use the standard expression. And then you use as local maps to bring everything back on the surface and do as if everything was flat. Okay, so now to introduce the second point, so I want to explain how you see the vertices. So let's say you have original 4-point amplitudes, and this 4-point amplitude, you can decompose it as follows. So first you will get contribution from the STU channels where you get a cubic interaction. So sorry, first you get a cubic interaction because you say that the cubic amplitude is directly the vertex. When you have this, you can build graphs where you get a cubic interaction, propagation of internal state, and again, a cubic interaction. And you can have it in the STU channels. But now the point that in general, the amplitude will not be reproduced by the 3 terms. So you need one more term, which is a contact interaction between the 4 states. And so you can define the contact interaction in your action just so that you recover the total amplitude. So in normal QFT, we don't really do that way. In normal QFT, we know the action, we write the Feynman rules, and then we build the amplitude. In string theory, it's the opposite. We know the amplitude. So from the amplitude, we can build recursively this diagram with propagators. And then we can just say that whatever remains is a vertex, the string vertex. So another way to write it is this way, so that you can write the amplitude as 3 terms, which are STU, and some vertex. And another way to see it is that, as I said, when you decompose amplitudes, so amplitudes are given by moduli space. So one way to decompose it is to just define subspace inside the moduli space. So graphically here, so you see that we get a covering of the moduli space of this way. So here's the example for the 4-puncture sphere where moduli space is just C. So because when you have the on-shell 4-point amplitude, you just integrate the puncture over C. So it's why we have this. Now, when you introduce this decomposition, you can show that the STU channels will each occupy some subspace around 0, 1, and infinity. But you see that you have a part of the moduli space which is missing. So this corresponds to V04. Okay. So now, to define the string vertex, you just take the expression you had before. But instead of integrating over M0n, you integrate over V0n. And that's all. You define your vertex in this way. And so, as I mentioned before, you define it so that at all orders, the sum of this vertex contribution and of the contribution from Feynman diagrams with propagators equals the amplitudes. So how you define the Feynman diagrams with propagators? You define them as any surface, which you can see as surface from vertex region in lower space, lower dimensional subspace, connected by a long tube. So you have two space, a long tube, and when you get together, like you should count all the punctures of all the subspace together. So you see it's why you will get n prime less than n. But again, if you think in terms of Hellman diagrams, it's kind of intuitive what it means. And also, I don't want to go into detail, but you have many constraints on the local coordinates. So you cannot just take whatever you want. So how do you build vertices now? So one family of vertices are the so-called SL2C. And they are arguably the simplest because the transition function are just SL2C maps. So it's very simple. So in Malan, for an equal 3, it's the simplest vertex you can get. For an equal 4, the boundary of V4 is analytic. So in fact, it corresponds to this diagram. So this diagram is what you get when you use SL2C functions. So in particular, these curves here and these curves are called Rimasson. And this one or ellipse. This one is an ellipse. The main problem is that it's quite hard to solve the constraint and get explicit coordinates. So we are still working on this. The n equal 1 torus was also solved for the boundary, but no explicit coordinate was provided. You can also use hyperbolic vertices, which are very promising. And then you have the minimal areas vertices, which arguably provides the best representation. I mean, together with hyperbolic. And you can see this minimal area vertices as some limit of the hyperbolic vertices at the classical level. And one thing I want to note is that, so you might have seen that I never spoke about the superstring. And the reason is that because for building vertices, the superstring doesn't really matter. Because in fact, you can obtain the superstring vertices by dressing the bosonic vertices with what are called PCOs. But generally, you don't really need to redo everything again. Like if you know the bosonic vertices, you basically know the superstring vertices. Another reason is that before, when I was discussing the momentum representation, again, for generic properties, it doesn't really matter if you work with bosonic or superstring. So what's more important is when you come to really like getting numbers. Okay, so I'm at the end of the string factor introduction. So if you have any question on that part, please ask. Okay, then I will move to an introduction on machine learning. So
just in case
yes.
you want to give a break or something, already we had a compulsory break somehow, but if you want, we can whatever.
Okay.
I mean,
I don't know what if you think it's better for participants to stop now. So as you see, I'm a bit less than half of the talk. So I can either go on for the machine learning and break after, or we can have 2 breaks also if you want.
Okay, I think from this side it is okay, but if you want to have a break, please.
Okay. Yeah, I'm good to continue. So I think I will do the machine learning and then we can break a bit.
Let's.
If it's good for everyone.
Okay. I think so. Yeah.
Okay, good. So machine learning. So one definition which I like because it's not like too restrictive and it's kind of broad and gives you a very good intuition of what it is. This one from Samuel, which says that it's the field which gives computers the ability to learn without being explicitly programmed. So I like this idea that it's so in standard programming, computer science, you just start with something, you give the rules, you write all the code. If you make a mistake, it's just debugs, and you take 2 days to debug, and then at the end you get something. Here in machine learning, it's different. It's more like you know what you start with, you kind of know where you want to go, and you say to the computer, okay, just find a way to do it. I don't care. And so it's really a different paradigm. So so here are nice graphics of how you can represent these ideas. So in classical programming, you give the input data, and you give the transformation rules, and then at the end you get some results. In machine learning is this, so you get the input data, the results, and you let the machine figure out rules so that you can reuse these rules in new applications. So how you do this? So the idea is to approximate some function y equal f of x by some structure. So it's this idea that you know x, you know y, and you want to find some f, which are the rules. So now like a function, you can just represent it in many ways. So for example, you can do a Taylor series expansion. You can do, like you have many expansion of various bases. But in machine learning, we use something like neural networks, decision trees, or even some set of decision trees, which are called random forest and so on. And one way to see this is that you start, so you have your input data X, and you want to get a new representation of your data from which it's easier to compute. So now this new representation can be the end result you want. So for example, the neural network is predicting exactly, so the output is really what you need. Or you can use the output to do some other computation which you cannot do directly on the input data. So you can mix this machine learning and classical programming part to achieve something. And so the agreement between the end results and what the machine learning gives you should be measured by some metric, which can be a distance, a constraint, or like anything you can use to describe, to measure how well it's performing. And the idea is that your structure will be will have some parameters which describe how it works exactly. And the idea is that you want to tune these parameters to improve the approximation. So I will give some more explicit example with the neural networks after. So we have different learning approaches. So the task is to go from X to Y. So first we have the supervised learning. So the idea is to learn a map from a set of pairs X trained to Y trained. So we just have many pairs which we know. We train some algorithm, and we get some structures to do this map. And then you can use this map on any new X data and make some prediction for Y data which were not known before. So this one is kind of the simplest to make work because it just works very well. People studied it a lot. The main problem is that you need to know the input and output, and if you don't know it, then you just get stuck. Or if you don't have enough data, for example. Then you have unsupervised learning. So the idea is that you get some X data, and you let the machine find the structure which gives you the appropriate Y data. So okay, here it's a bit like it's not the best way to phrase, because like again you can split the X in train and data, so you can train your algorithm with some training part and then use it on new data also. And finally, you have reinforcement learning. So here the idea is that you get some X data and you let the machine choose some output according to some rules, and you reward the good results and you punish the bad ones, and then the machine will learn to change the rules to find the result, and you iterate over and over. So reinforcement learning is quite good for physics and math, and I think it will be one of the most used when we understand how to manage it, because it's very easy to work with symbolic data in reinforcement learning. It's a bit harder with supervised and unsupervised. So the general idea of machine learning is really pattern recognition. So you have some data, you want to find some pattern, which might be hard in your initial data. So you just use the machine learning algorithm to provide a new representation for which it's simpler to do all the different tasks. So what we can use in physics, which can be useful, are classification, regression, which is prediction of a continuous variable. We can imagine some anomaly detection to find like a counterexample to some theorem. Density estimation, for example, if you work in the string landscape, and symbolic regression to extract analytical formula from numerical data. Okay, so now let me move to neural networks. So what is a neural network? So you can see it as a sequence of layers, each implementing some computation. Now the idea is that each layer gives you a different data representation as an output. So in some sense, like, so I was saying that machine learning is really like finding a structure to make you a new representation. Neural networks brings this in a bit more like microscopic way, because at each intermediate step, you can understand this as giving you a new representation. So you get a new representation, which you transform again and again. And it gives you a lot of flexibility, because like if you start to transform, at any point you can start to branch and do again new computation and get different representation, which you will reuse for different things later. The transformation applied by each layer is parameterized by some weights. And the goal is to find these weights here such that the network reproduces the target. So as you see, we have some input data, we pass in different layers and we get some predictions. And we want this prediction to be equal to the true results. So how we do this? So we need to compare everything with an objective function. So the objective function must take the prediction. And then it can take the true results and all the input data to compute its value. So it really depends about what you want to do. So for example, if you want to do which is not supervised, you need to just give the input data and the prediction. If you do supervised, you will compare explicitly the true and the prediction. So you will give these two. So it's just a lot of flexibility about how you can design this objective. This objective function gives you some score, because you will evaluate it on many examples and take some average. And from this score, you try to bring it to 0 using some optimization process. So when you do the optimization, you just update the weights so that you get the score closer and closer to 0. So this optimization is done using gradient descent. And now the final point is that this general architecture here is parameterized by what we call hyperparameters. So it's the number of layers, the type of layers, like the details of the computation, and so on. Even the objective function, for example, can have some parameters. So just every parameters which are not weights are called hyperparameters. Why do we want to use neural networks? So the point is that generically they outperform any other machine learning approaches. But it's not always the case. So for example, it's always important to start with some good validation using like linear regression or some simple model. Because if you find that your neural network performs worse or as good as linear regression, you should not use it, because it's just a waste of resource and time. Another motivation is that the inputs are very flexible, so you can feed just numbers, matrices, tensor, complex number, even graphs. So text. So you can really just feed whatever you want. I mean, not whatever, but a lot of data, which you cannot do with most other algorithms, which take mostly tensors. The neural network is a differentiable function. So this is very interesting. So recently there is this idea of differential programming. So the idea is that when you do programming in classical programming, whatever you write is just some function, and you can evaluate it let's say you write a square function in Python. You can evaluate it for different numbers, but if you want to compute the derivative of that function, you cannot do it because it's just some code which is written in some way. So you need to either like do a finite difference derivation, or you need to hardcode yourself the derivative function of the square, so 2x. Now in differential programming, the idea is that whatever you write in your code should be a differentiable function of its inputs. And now it's very powerful, because you can just start to write some expression, and if you want to get derivatives, you can just take derivative. In particular, if you want to optimize with respect to some parameter, you can just do it very easily. And so one very prime example of this paradigm is our neural networks, which are represented in this way. So in particular, because it's a differentiable function, when you have it, is that you solve for the full function. It's not points one by one. So even if during training you just use discrete points, the object you have in your code at the end is a function which you can evaluate for any inputs. So it's much more expressive. It's better than a fit, because the fit, you need some points and it will try to move. Here the function is able to extrapolate outside the training region sometimes. So it's a better approximation overall. And also the nice point is that a classification task provides you with a probabilistic measure. So now if you want to do some integration with respect to some measure, you can use this probabilistic measure and do some Monte Carlo or something, which you cannot do when you just have points. I mean, you can, but it's more painful. You can do also transfer learning. So for example, if you train a neural network to achieve one task, it's quite easy to just take the neural network, remove the head, add some fresh head, and reuse it for a new task. So you can. So for example, if you train a neural network on text translation, you will find that it's able to do many other tasks related to language, even if you didn't train explicitly for that. So for us in math and physics, it can be interesting, because imagine you train a neural network to do some task on the model space. Now you want to compute some other function. Instead of doing the training from scratch, you can just start at some intermediate step. And then also a very compact representation of the result, which you can easily use, reuse, and share. So it's much better than just storing single values. Okay, so to go more in detail, let me give an example of a fully connected neural network. So neural network, we have this shape. So you have some input. So here it's 3-dimensional. You have one hidden layer, which is here 4-dimensional, and you have the 2-dimensional output. So how does it work? So the first, we have the input layer 0, which has some parameter. So to move to the next layer, what we do, we take this input vector and we multiply by a matrix of weights, which correspond to the first input layer. So this W1 corresponds to all the arrows here. So this matrix multiplication, then you shift by some vector, and you apply some nonlinear function G. So here the weights are just the weights of the network. B is called the bias, and then the G is called the activation function. So in principle, you can tune all of this to improve your results. Now the point that using a function is in general not a continuous choice. So this one, you cannot optimize it by gradient descent. So this is something which is part of the architectures, and you can even fix this. So you can consider this as one of the hyperparameter. And in the gradient descent, you will tune the W to achieve a better result. So okay, so you have done this for the first layers, and you can do it for the second layer. So again, you take the vector you obtained previously, you multiply by some weight, you again shift, you apply a new nonlinear function, and you get some x2, which is the function of the inputs you want. So now in this process, so as you see, it's a very simple network. You tune W and B so that this function is as close as possible to the function you are looking for. Okay, and so in general, you don't get one hidden layer, but you will get many more. But the idea is just the same. You just continue this process until you reach the last one. Okay, how do you train such a network? So first, you need to fix the architecture, so the number of layers, the activation function, and everything, like the type of layers. Then you want to learn the weight from gradient descent. So how does it work? So you need to find some loss function, which is like an error to be decreased. And one simple instance, when you know so you do supervised, you want to compare the train and the prediction. So you need to find some distance. So it can be the mean squared error, or the cross entropy, or anything. And you can also add regularization, which is something which prevents the weights to be too big, because you don't want, weights to be arbitrarily large. You want to keep them small. Then you need to define an optimizer and its parameters, in particular the learning rate or the momentum. So the idea of the learning rate is that when you do the gradient descent, you need to specify the size of your steps. So you can do small steps or larger and so on. And momentum will keep you going in the same direction as before. So imagine, okay, I don't know if you see we're in 3D. So imagine you do a first step like this, but the second step tells you to go like perpendicular. You might say, okay, it's weird because I just go back from here and then I go back a bit behind. So maybe it's not a great idea to just wind in this way. So instead of doing this, momentum will tell you, okay, I will take this vector, but then I will also add a small portion of the one before, so that in fact we move more like this. So momentum is kind of trying to keep going in the same direction because you're like, okay, if you saw it before that it's a good direction, you should not just forget about it immediately. Okay, so weight regularization, remove redundant weights. And then you need also to define a training protocol. So like, when do you want to stop? Do you want to change the learning rate during training and so on? So all these are choices you make, which are considered to be hyperparameters, which are fixed when you do the first training. The next step, when you have done the first round and you see a bit what happens, you want to improve all the hyperparameters. So as you see, it can be dozens of parameters, so it's a bit difficult so you cannot do it systematically. To just improve the results more and more, because like gradient descent will get as close as possible, but if you have bad parameters, it will just not work well. And when you want to reach few percent or even like 0.001% accuracy, you will need to go in this tuning. So you have various search methods like trial and error, grids, random, genetic, and so on. And the main risk of all this procedure of trainings and doing hyperparameter tuning, training again, and so on, is that you will overfit. So by overfitting, it means that you will not generate new data because your network has learned by heart the training data. So for example, if you look at this, the real data is like small noise on this line. But if you have a neural network which is too powerful and you really trained a lot, it will try to pass exactly through each point, but giving you a function which has nothing to do with the original function. So for example, imagine if here you get a point you take here and which will be there with a noise, you see that we get a huge error in the prediction. So it's not a good model. So how you do to avoid this? So you need to split your data in 3 different sets. So training, which you just use when you train. Validation, which you use when you do the hyperparameter tuning. And test, which you keep until the very, very, very end, and which you use to evaluate the performance of the best model you have ever found in all this process. In this way, the test set is really like a new set of data which has not been seen before, so you can read and you can trust better your results. And one interesting thing to do is to train n models in parallel to get the statistics. So to know, like, because you don't want to just give the best results, you want to give like representative results. It's good to have a few networks at the same time to do this. Do you have any question for that part? Okay, so if not, now I want to describe a bit more the different components you can find in neural network, just to show that this simple example I gave of fully connected, when you just get a vector, you multiply, shift, and so on, you can get more complicated things. So for example, you can have convolutional layers. So here the idea is to move a window over the data and combine the value with the kernel. So for example, if your kernel is 0, 1, 2, 3, the input is this. To get the output, you multiply each like box with the one of the kernel. So if you do 0 times 0, 1 times 1, 3 times 2, and 4 times 3, you find 19. Can you hear me? Can you hear?
Yes, we can hear you.
Hello. Hello.
We can hear you now.
Okay.
Okay, I cannot hear anyone. I don't know why.
Okay.
Can you hear?
Let's start the. I can hear you. I can. I do. Oh, can you hear now? Can you hear me now? Does anyone here can hear me? Can
Yes, we can hear you.
okay. So,
نمیدونم فکر کنم از آی پی ام بنده خدا باز دوباره
الو. صدای من میاد؟
آره صدای شما میاد آیدس.
فکر کنم ایراد از طرف خودش هست.
آی دکتر این صدا شما داشتیم، این بنده خدا صدای ما رو نداشت.
آره نکته مخفولی که تو این داستان بود این بود که ما تصورم بود که من اول تصورم بود که این قطع نمیشه و دوم که قطع شدنش هم فکر می‌کردم با لینک مجددا با همون لینک قبلی قابل. اوکی. Can you hear me now?
Yes, now I can hear.
Okay. So let's
Sorry
start
for the pain.
yes, the last part of the session. Please go ahead.
Okay, so now I will move to describe the minimal area string vertices which we want to use to write a string field action. And then after this, I will explain how we can define them with machine learning. So what are the minimal area vertices? So it's a vertex which is constructed from a minimal area metric with bounds on the length of the shortest closure desix and the height of internal foliation. So what does it mean? So it means that on each Riemann surface of your modular space, you get the metric, and you want this metric to have the lowest area as possible given the other bounds. So the other one, so first you have some geodesics on your surface, and you want this geodesics to not be smaller than some size. So the idea is that you don't, so if your geodesics goes very small, it means you have a very short cycles. You don't want to see something if you want all your cycles to be bigger than something. And then the internal foliation, so the height is kind of like some distance like this. So what does it mean that when you have some a big, so a large internal foliation, it's like a tube. So it means it's like a propagator. So any vertex which is minimal area must have only very short tubes or no tube, and it should have no small geodesics to prevent this, like because you don't want small cycles. And now the point that if you look at n-puncture spheres, you can construct this metric from Strebel quadratic differential. And the nice point is that the differential is fixed up to moduli dependent parameters. And they lead to contact interaction in the sense that you not have any internal foliation. So you all internal foliation have H0. So it means you don't have any tube or anything. It's just like as close to a contact interaction you can have for a string theory. So the goal here is to get all the local coordinate for n larger than 3 and the vertex region. So we want to go as high as we can because the higher we go, the best will be the approximation of the potential and of the effective actions. And so the state of the art is as follows. So the solution is analytic for n equals 3. So in fact, it's a generalization of the Witten's vertex from the open string. And it's numerical for n equals 4 and 5. So it was done by Maurer almost 20 years ago. And it's also worthy to note that the 5-point result was not given as fit or anything, and the data has been lost. So in practice, if you want to work with that now, you just have n equals 4. There's also a convex program which works for any genus and n in principle, but it has not been implemented concretely, and it has not been shown how to restrict to the vertex region. Okay, so what is a quadratic differential? So a quadratic differential is something of this form. So you have a phi of z dz square, so where z is a coordinate on the sphere. And we are interested in differential which have this form. So you have a double pole at each puncture location with residue -1. And then you have a simple pole at each puncture with some, where the residue is some parameter ci, which is accessory parameters. And the point that by demanding regularity at z equal infinity, we get 3 relations between the ci. So we just have n-3 of them available, which are not fixed. And it's exactly the same number as the number of moduli. So there is kind of a relation between moduli and accessory parameters. And when you have phi, so it also induces a metric with summary infinite flat cylinders on each of the punctures, which are external strings. So the metric is given by this, so this phi z square. And so in the local coordinate page and close to the punctures, it takes this form, which is a metric for a cylinder. So it makes sense because you want to imagine your surface, so you have your sphere with punctures, but if you go close to a puncture, what you want to see the surface like is something with a long tube which goes to infinity because it's your incoming string which goes there. Also, why this thing is nice, because if you start with just some generic local coordinates, you need either to build local coordinates, so you have one for each punctures, and they depend on the coordinate on the sphere. So it's a lot of information. You can also get a metric, and from the metric extract local coordinate, but in the same way, the metric, it's a full function. Here in the quadratic differential, everything is fixed except the CI. So you have much less things to compute. So it's why it makes the problem much simpler. So now I need to introduce some terminology. So first I will call ZI the zeros of phi. Next, so I will call it trajectory. So trajectory is just some lines which go between the point Z and some other points, and an infinitesimal movement will be called dz. So here, for example, it's some example of trajectory. And I will call a horizontal trajectory, which is a path, shows that the quadratic differential is positive. So what's important is that it's 3 phi z dz square, which is positive. So what are some examples? So here you have one, which is just dz square. So as you see, like it's always positive. You have z dz square. So here you can see that you have some place where the lines will meet, so which correspond to z equals 0. And then you have a concentric circle for minus dz square over z square. So these two will be very interesting for us because this, in fact, it just so it will give the metric of a semi-infinite flat cylinder. So we expect that the Strebel differential should look like this, close to the puncture. Okay, so in fact, it's why here we have this term here, because this gives something which are like concentric circles, so this will be tubes. Now why is it interesting? Because now if you look at the surface and you have such a place, you see that it will split the surface in different regions, where each will have some line like this. So now you can imagine that if you combine with some concentric circle, here you get some concentric circles, here also and here also. So this will split the surface in the regions where you have different strings. So here is an example. So, okay. Before moving to the graphics, so a critical trajectory, so it's a horizontal trajectory with ends at zeros of phi. And then the critical graph is a set of all possible critical trajectories. So here it's an example. So you have the sphere, you have 4 punctures, and you have 4 zeros. And as you see, like all the lines are the critical graph. And as you see, the critical graph is separating the sphere in different parts, where in each case you just have 1 puncture. So now you can also project on the plane and you will get this kind of diagram. And now I can define a Strebel quadratic differential. So it's a differential such that the critical graph is a polyhedron, so it has measure 0. The vertices correspond to 0, the edge to critical trajectory, and the face to punctures. And it's connected, so there is no propagator on long tube. So you could imagine the graph to be like in 2 parts, and for example, with just 1 line in between. This would be a propagator. You don't want that. Now you can show that the Strebel quadratic differential is unique given the moduli, that it defines the minimal area metric, and for this reason defines the string vertices, so you can extract local coordinates and also get the vertex region. Okay, how do you get the accessory parameter? So it's a hard mathematical problem, so it's related to the function uniformization and Euler theory, so it's not something you can do easily. So to do that, first we define the complex length between 2 points. So it's not a proper length in the sense that it doesn't give a distance. Because you see, so integrate between some paths between A and B with the element dz. And you have the square root of phi, and phi here can be complex. So it's phi here, it's a complex length. Now, what you can show is that for Strebel differential, a necessary and sufficient condition is that the imaginary part of this complex length between any two pairs of zero is zero. If you remember the zi or the zero of the phi. So if you have these conditions, that you know that phi is Strebel. Why? It's because we know that on the critical graph, as we have seen here, phi is positive. So if you take the square root of this quantity, it's also positive and real. So now if you integrate this quantity over any path where this holds, it should be real. So it's an explanation why we have this condition here. So for fixed moduli, we get equation on the CI. And what Maurer did was to solve point by point using the Newton method for an equal 4 and 5, and to give a fit for an equal 4. So as you see, it's very cumbersome because you need to do it one by one, get points, list all your points, and then try to compute whatever you can with these points. Okay, so how do you get local coordinates? So the idea is that the way you get them is that you can map so the unit circle, of the local coordinate patch, the critical trajectory, the corresponding curve. So now you do a series expansion. So you have your local coordinate match, which you expand. So as you see at zeros, you should recover the puncture. Then you have some scale rho I, which is called the mapping radius. So here it means you cannot just fix it from the series expansion. And then at higher powers, you have some coefficients there. Now, if you take the quadratic differential, you know it's written in this way. You can expand the single pole around the puncture with some coefficients. And now you want to match this series expansion with expression in the local coordinates WI. So what you do now is that, so here you have this expression for Z, which you can plug in this expression. Here, and now you compare the two, and this will give you some relation for the between the BI and D. So for example, you have these kind of things here. Okay, and you have the mapping radii, so which is not known, so you need also to compute it. So here we found a nice trick which make it simpler to compute compared to Maurer's. So it's again just some integral of the complex length over some path. And I will not go into the details, but basically you need to compute the distance between the punctures to any zeros of the critical graph. And the point is that, and the imaginary part of this length is related to the mapping radius. So now you can take any zero, because in fact, even if you take, so if you take a zero which is there, so okay, there is nothing tricky. If you take a zero which is not on the critical graph on the punctures, it looks like you get contribution from that part, but also from here. But in fact, this place does not contribute because you can just define the path to move along the critical trajectory. So this will not contribute to the imaginary part. So the mapping radius, how you can interpret it, is kind of the radius between the puncture and the boundary of the critical trajectory. So now you can get the vertex region. So it's defined by any point in the model space, such as the length of non-contractible curves are larger than 2 pi. So I don't want to go into the details, but the idea is that if you start to get lengths which are smaller than 2 pi, when you will grow, you will generate graph with so you will have a problem with the graph you generate. You will not generate the graph you would expect to be represented by some propagators. So you need to start with this constraint. So the first thing you need to do is to determine the shape and the distance on the critical graph. And then you can compute the length of any non-contractible curve. And for example, for an equal 4, you can show that you get this constraint on the length A1, A2, A3, which so we're given here. So here you have A1, A2, and A3. So you can show that they should be all larger than pi. Okay, and then when we have this, we can define an indicator function. So it's a function which gives you 1 if psi is in the vertex region and 0 if it's outside. So the idea is that you can then replace any integral over the vertex region by integral over moduli space with this indicator function. Okay, so is it clear for all these definitions? Okay, then I will continue. So again, like all those details are not very important. Like it's in the paper, you have all the formulas and you don't need to understand them in full details to just be able to code and understand the code. The main option is that you have a nice mathematical structure, which is very rigid when you look at minimal area vertices. So it's very helps to make the computation. So now we want to compute the accessory parameter and so, okay, what do you mean by the dictionary between ML and SFT?
Sorry, what's the point? Can you continue? Or?
Oh yeah, I was wondering if Madi wanted to ask more about his question. So,
So Mahdi Mansouri, are you asking a question now? Or? So his question is, what is the dictionary between machine learning and
so I'm
I
not sure
guess
to understand exactly what it means. If it's
I think
how
the
we use
idea
machine
is
learning.
right. Can you explain what you mean by the question? I think the idea of Harold is to explain exactly the same thing.
Yeah, I think if the question is how I use machine learning in string factory, it's the goal of this section. So like if it's this,